In my thesis, part of my thesis is searching for exocometary activity in debris disk. Debris disks are circumstellar disks, disks of dust and pebbles surrounding stars. And exocomets are comets outside the solar system, and they can also be found in the interstellar medium. When searching for the activity of exocomets, I'm looking particularly for the gas, the atmosphere of the exocomet. When the exocomet approaches the star, it gets warmer and evaporates and produces this atmosphere called the coma. And this gas is what I detect in my study. Let's talk about debris disk. We start with a molecular cloud of gas and dust, and because of gravitational instability, this cloud collapses and forms a globule, and because of the angular momentum, this globule is going to start to rotate. Then, with the years, the spinning will increase, making this globule to flatten and cool down and transform into a protoplanetary disk. Well, you've seen this before, a protoplanetary disk, a beautiful one. This protoplanetary disk is going to evolve for 10 million years, while all these processes have something to do with planet formation inside the disk. And the three main responsible for removing the gas out of the system are accretion, photoevaporation, and radiation pressure. This protoplanetary disk at the beginning is 99% gas and 1% dust. But after 10 million years, that 99% of the gas should be removed out of the system and leave us with only the solid particles, the dust, planetesimals, asteroids, possibly formed planets, possibly gas giants that formed earlier during the gaseous stage of the disk, and comets. So as I said, debris disks, by this stage, they are not supposed to have gas anymore. But in the last few years, it has been found gas in a few debris disks. For instance, this CO emission found with ALMA. And this gas, there are two possibilities. It might be residual gas from the earlier stage of the disk, or it might be second generation gas, which can be produced by exocomets, by collisions between dust particles that contains volatiles, or just exocomets evaporating inside the disks. So in my study, I'm using optical high-resolution spectroscopy, which is really good for tracing small amounts of gas, particularly the absorption lines of ionized calcium and sodium. And at the left, you can see this absorption is the absorption produced in the photosphere of the star. This is the stellar absorption of calcium. Fully evaporating bodies, which are the same as exocomets, were first detected in Beta Pictoris system, which has a debris disk and a planet. And as the comet approaches the star, it produces these variable absorption features. And as the gas accumulates inside the disk, it will produce a stable absorption at the very same radial velocity of the star. And it's going to be part of the system. Well, the main purpose of studying this exocometary activity and the gas in the disk is because gas affects planetary formation. The dust particles, they couple to the gas, and the gas drags all the different pebbles and bodies and dust in the disk, so the dust follows just where the gas moves. And as it changes the dynamics in the disk, it can also affect the morphology of the disk. It might form gaps or asymmetries that may or may not increase accretion and planet formation, but it affects it. And it's also interesting to study the volatiles transport within young planetary system, because the volatiles that are present in comets, they contain organic molecules, amino acids, and they may have something to do with the beginning of life. We don't know, but we still need to study it. I am analyzing a sample of 301 debris disks with ages over 10 million years old, so they shouldn't have gas anymore. They all have been observed with IRS Spitzer, And I call this sample unbiased because it is not selected in terms of inclinations. We don't know most of the inclinations of the disk, so it's unbiased in that way. And this is kind of key because we need the inclination to be edge-on like this in order to detect the exocomets crossing in front of the star. If the disk is face-on, the comets are going to be here and you won't see them crossing the star. And as you can see, it has a wide range of spectral types from B to M because we want to know what kind of star have this exocometary activity. I found 27 candidates with multiple absorption features, which is the most interesting group because by having multiple absorptions, we increase the chances of having circumstellar gas and exocomets. And why do I say if it was circumstellar? Because all of these absorptions are not necessarily circumstellar. They can also be produced because of the interstellar medium. In the interstellar medium, there are clouds of gas that cover the star and also produce very, very similar absorptions. So it's kind of tricky to distinguish the origin. And I follow certain rules. So circumstellar gas, it could present or not present variability, but interstellar gas is going to be stable all the time. This gas, circumstellar gas, should be near the radial velocity of the star because it belongs to the same system, so it all should have a similar velocity. And you'll see these sporadic absorptions which are not going to be caused by the interstellar medium, only because of exocometary activity. And the composition also should be more heavier on calcium than sodium, but that's a very general rule and there are exceptions. So I isolate these narrow components. I model the photospheric part of the line and I isolate these narrow features to study them and measure their parameters, like the radial velocity to know if it's close to the radial velocity of the star, their signal-to-noise ratio, density, equivalent width, to know about the composition, if it's more heavy on calcium or sodium. And in addition, I analyze all the stars in the neighborhood surrounding my target. Because if there's an interstellar cloud in front of all these stars, it's going to produce an absorption in all of them. So I study the neighborhood. And for instance, at the left, there's an absorption common in all these different stars. But the red one, which is my target, it's the only one that has an absorption, and it's close to the radial velocity of the star, which is marked by that vertical line. So that one is circumstellar, and the left one is interstellar. I also analyze all the different epochs, different observations during different nights, and the black part is the average spectrum, so I have a reference to compare to, and all the different color lines are different observations. In the left object, I have variability at the very same radial velocity of the star, which is marked by the vertical line. So it means that the density of gas in this object has been changing, so there is activity there. And a very interesting object is the one in the right, which has redshifted activity, high activity, strong variations in flux. And it's redshifted because when you look at the star and the comet falls towards the star, from the point of view of the observer, the velocity is going to be redshifted, so you see it at redshifted wavelengths. And let's take a look in more detail to this object. For instance, in the first epoch, let's set the time to 0 there. After a couple minutes, this 3.8 sigma absorption decreases, and after 3 minutes, it decreases even more, and after 4 minutes, it's completely gone. So this event lasted only about 3 minutes. It's a very fast event, and it's really cool because it's the fastest with the shorter time range event that I found so far. Short events have been found in Beta Pictoris, but they last about 1 hour, 1 hour and a half, and this is really, really fast, only a couple minutes. It's really cool, and I will keep researching this object. I will perform a more detailed analysis of this exocometary activity, try to trace the orbit, the location of the exocomet population, and I'm going to look for more of these kind of events in more objects of my sample, and perform follow-up studies of these, the most interesting objects, for instance, photometry, or try to obtain ALMA data, try to resolve the disk and see the actual inclinations, and yeah, keep studying. Thank you.